So last time we introduced the absorptivity of a layer of gas. This time we're actually going to figure out how to calculate the absorptivity of a layer of a gas. So we have a slab layer that has a thickness dz, and we have a certain amount of radiation which is going to be passing through this sort of thing, which is the irradiance F of lambda. It's going to be passing through, and as it passes through, it's going to be reduced. So we have F of lambda plus or minus d F of lambda, so that we have a smaller amount of radiation after it has passed through this absorbing gas. So the change in the absorptivity is minus d F of lambda over F of lambda is going to be equal to minus k lambda times density times the secant of the zenith angle times dz. Recall that phi is the zenith angle, and it's the angle between the incident radiation and the area and the direction orthogonal to our surface that the radiation is passing through. K lambda is the absorption coefficient of a particular gas. It has units of meters squared per kilogram, and it's something that's measured in the laboratory. Unfortunately, it is a function of pressure and temperature. So for a given gas in the laboratory, you would have to take measurements of that gas as a function of temperature and as a function of pressure in order to get the absorption coefficient for those two-dimensional sort of absorption coefficients. The density is not the density of the air, it's the density of the absorber. This is the most common error that's made when doing a calculation of the absorption by a gas. And then secant phi dz is actually the path length of the radiation through this absorbing layer. So the absorptivity, using that definition over there, would be the integral over the change in the absorptivity from the top of the atmosphere to some height down further into the atmosphere. We'd integrate the minus df over f, and we'd integrate this minus k rho secant phi dz. So the integral of df over f is just the natural log of f, evaluated these appropriate limits. The secant phi is a constant. But K, the absorption coefficient, and the density of the absorber are likely to vary significantly with height. The absorption coefficient because it's a function of temperature and pressure, and the density of the absorber just because we probably don't have a constant density of that absorber in the atmosphere. And we're going to simplify our life a little bit and take this entire quantity that's integrated from the top of the atmosphere, infinitely high, down to some height, as the optical depth of the atmosphere, and we're going to use the symbol sigma, which is not to be confused with the sigma which is used in the Stefan Boltzmann law. That's a constant. This is the optical depth of the atmosphere. Mathematically, we can evaluate the natural logarithm of these two limits. We have a negative sign out here in front. We can incorporate the negative sign into the natural log, flipping the numerator and the denominator, and solving for the the irradiance at a given height in the atmosphere. And the irradiance at the some level in the atmosphere is equal to the irradiance at the top of the atmosphere times the exponent of minus the optical depth of the atmosphere, and recall that the optical depth is this quantity up here. And we refer to this as Beer's law. And we'll see here in a minute that this can be expanded to include not only absorption by gases, but absorption by particles and scattering as well.